Sampling distribution of the mean. Part 1, population. Suppose a fair die is thrown an infinite number of times. Then the population for this experiment is the infinite number of outcomes that would be obtained. In this case, the proportion of the time that each of the numbers 1, 2, 3, 4, 5, and 6 occurs will be equal. This is why we say that the probability of each number is 1 over 6. So 1 over 6 being the total, there are 6 possible options if you're rolling a die from 1 to 6. If the random variable x represents the outcome when the die is thrown, then we can construct the following probability table for x. So if x is 1, the probability is 1 over 6. If x is 2, if our outcome is 2, the probability of x is 1 over 6, and so on. So we see we have equal probabilities, each at 1 over 6. Then the mean, or the expected value, is given by 1 times a sixth, plus 2 times a sixth, plus 3 times a sixth, plus 4 times a sixth, plus 5 times a sixth, plus 6 times a sixth, which is 3.5. So multiply each of these and add it on to each. So our expected value is 3.5, or a mean. Also, the standard deviation can be calculated by treating the probabilities as frequencies. So we're going to use our standard deviation formula. So we take our x value, which is 1 to 6. We subtract the mean, which is 3.5. So we see 1 minus 3.5, 2 minus 3.5, 3 minus 3.5, 4 minus 3.5, 5 minus 3.5, 6 minus 3.5. Then we square it, so we can see the squared. And then we multiply it by our frequency, which in this case is our probability, which is a sixth. So we have a sixth in front of each of our brackets. And the symbol sigma means to add, so we add them. And it's divided by the sum of the frequencies. Again, the frequencies in this case are the probabilities. So we add up the probabilities, which are all 1 over 6. So we end up getting a sixth times 6.25 plus 2.25 plus 0.25 plus 0.25 plus 2.25 plus 6.25. And technically it's all over 1 because adding 6 sixths gives us 1. And we end up with 35 over 12. And then all we have to do is apply the square root. And the square root of 35 over 12 is 1.7078. So we got that formula on page 33 of our tables for standard deviation. So from a frequency table, in this case we're using a probability table, so this is our formula. So again, here's our probability table. This probability distribution is not normal. So if it was normal, we would have a bell-shaped curve. In fact, because the probabilities are all equal, it's called a uniform distribution. And its histogram is shown below. So a normal curve would be bell-shaped and symmetrical. But in this case, we have uniform distribution, so it's just a block. And they all have an equal probability of 1 over 6. And the mean lies here, 3.5. And the standard deviation we worked out to be 1.7. So 3.5 plus 1.7 would be about here. Part 2, single sample. Now suppose we take a single sample of a reasonable size, say 10, 20 or 100. It is not reasonable to expect the distribution from a relatively small sample, like this, to be an exact replica of the overall population. For example, in one experiment, a die is thrown 60 times, and the frequencies of each of the numbers is shown in the table below. Also shown is the experimental probability, the probability of x, obtained by dividing each frequency by 60. So our x values are from 1 to 6. The frequencies, for example, we landed on 1 13 times, we landed on 2 12 times, and so on. So these are the frequencies. We roll the dice 60 times, so dividing 13 by 60 gives us 0.217 for the probability, which is the relative frequency. Dividing by 12 by 60 we get 0.2. Dividing 7 by 60 we get 0.117. Dividing 11 by 60 we get 0.183, and so on. The distribution may be illustrated in a histogram shown below. So, for example, the probability of landing on 1 is 0.217, which would be about here. The probability of landing on 2 is 0.2, which is here, and so on. On a point of notation, while the mean and the standard deviation of a population are generally written as these symbols respectively, the mean and standard deviation of a sample are usually denoted by X bar and S. So X bar is the mean of a sample and S is the standard deviation of a sample. This is important. For this experimental data, the mean X bar is 3.27 and the standard deviation S is 1.75. These are not exactly the same as for the population, but they're not far away. It is also important to note that if this experiment of throwing a die 60 times is repeated, the outcome is likely to differ from that of the first trial. If we take larger samples, then the distribution is likely to be closer to that of the population. We can investigate the effect of taking larger samples by using computer programs such as Excel. Using such a program to model a large number, for example 21,600, of dice thrown, one set of outcomes is as follows. This gives a mean of 3.523148, standard deviation of 1.7086, and both are very close to the theoretical results obtained previously. Every time the program is run, different but similar results are obtained. Sometimes the mean is slightly above 3.5 and sometimes slightly below. Otherwise, with the standard deviation, sometimes it is slightly above 1.7078 and sometimes slightly below. Part 3. Distribution of the sample means, also known as sampling distribution of the mean. Now suppose we consider many samples, all of the same size. Let's say size 36. Suppose we just record the mean of each sample and nothing else. Say they were X bar 1, X bar 2, X bar 3, ... So here we are recording the mean of each of the samples. If we draw a curve to represent the distribution of these sample means, something astonishing happens. The distribution satisfies some interesting and important properties as long as we take enough samples of the same, sufficiently large size. The following observations can be made for the distribution of the sample means. Number 1. The distribution of the sample means is always approximately normal. So that means a bell-shaped symmetrical curve. The larger the size of the samples, the closer the distribution of the sample means will be to a normal distribution. Most statisticians agree that if the sample size is at least 30, then the distribution of the sample means may be taken to be normal. So they have to be at least 30, the sample size. Number 2, the mean of the distribution of the sample means, written as the mean symbol with a small X bar stuck beside it, is the same as the mean of the population. i.e., the mean of the distribution of the sample means is equal to the mean. Number 3, if the standard deviation with a little X bar stuck on beside it represents the standard deviation of the sample means, then the standard deviation of the sample means is equal to the standard deviation divided by root n, where n is the size of the samples. So this symbol here is called the standard error of the mean. and it is given on page 34 of the formulae and tables. So here we have page 34 of the tables, and we see under the sampling section we have standard error of the mean. So again, here we have our histogram. So the population is all possible throws of the die, and the probability of landing on 1 is 1 over 6, the probability of landing on 2 is 1 over 6, the probability of landing on 3 is 1 over 6, and so on. So the mean is right in the middle here, which is 3.5, and this is the standard deviation. So this is for the population, all possible throws of the die. Here we have the distribution of means of sample size of 36. And we can see that we have a normal curve. The mean, again, lies in the centre, it's 3.5. And to get the standard error of the mean, it's the standard deviation divided by the square root of n, which is the sample, which in this case is 36. And the square root of 36 is 6. So it's the standard deviation divided by 6. These properties are contained in a theorem called the central limit theorem, which can be mathematically proved. This is a very powerful and far-reaching theorem, which has a number of different forms depending on conditions. The version we use on our course is given below. So here we have the central limit theorem. So suppose a population has this for a mean and this for a standard deviation. Let x bar be the random variable representing the means of all samples of size n taken from this population. Let this distribution have a mean of this and a standard deviation of this. So basically it's the mean with an x bar stuck on and the standard deviation symbol with an x bar stuck on. So number 1, x bar is taken to be normally distributed for n greater or equal to 30. So we can only say that it's normally distributed if n, the sample size, is greater or equal to 30. So the mean of the distribution of the sample is equal to the mean, and the standard error of the mean is equal to the standard deviation divided by root n. For the example given above of the samples of size 36 throws of a die, the central limit theorem applies because 36 is greater than 30. The diagram above shows the relative frequency histogram for the population and the curve representing the distribution of the means of sample size 36. So a reminder again, here's our histogram and here's our curve. For samples of larger size, for example 100 or 1000, the distribution of the sample means has an even smaller standard deviation. If the population is itself normally distributed, then the central limit theorem applies even when n is small, i.e. even when n is less than 30. Because the distribution of the sample means is normal, we can use the standard normal tables to calculate the probability that the mean of a sample of a given size differs from the mean of the population by a certain amount. So let's have a look at an example. Bags of flour are known to have a mean weight of 2 kilograms and a standard deviation of 50 grams. Part 1. If a sample of 100 of these bags of flour are chosen at random, what is the probability that their mean weight is less than 1.99 kilograms? It is important to recognize that the key distribution we have to deal with is the distribution of the sample means, which is normally distributed. We know it's normally distributed because the sample size is 100, which is greater than 30. We need to determine its mean and its standard deviation. Then we can convert 1.99 to standard units and use the standard normal tables to calculate the probability. Okay, so the population, which is all bags of flour, We're told in the question the mean is 2. So the mean is 2 kilograms. The standard deviation is going to be 0.05. Because we're told in the question the standard deviation was 50 grams, but we have to convert that into kilograms, so 50 grams equal to 0.05 kilograms. Okay, so the distribution of the sample means for samples of a size 100. So remember, the mean of the distribution of the sample means, written as the mean with x bar stuck on, is the same as the mean of the population. And that is equal to 2. So that was again given in the question. And the standard error, which is a formula given on page 34, is the standard deviation divided by root n. The standard deviation is 0.05 and n is 100. And 0.05 divided by root 100 is 0.005. So this distribution is normal because the sample size is 100, which is greater than 30. So we're going to use an x value of 1.99. We're going to use our standardizing formula from page 34, which is x minus the mean divided by the standard error, and x is 1.99, so 1.99 minus 2, which is the mean, divided by 0.005, which we worked out over here. And that gives us minus 2. Thus, the probability that x is less than or equal to 1.99 is the same thing as the probability that z is less than or equal to minus 2. We can't use minuses in our standard normal tables, but we know that our normal curve is symmetrical. So this is the same thing as z greater or equal to positive 2. And we can only ever work with less than for our standard normal tables. So it's going to be 1 minus the probability that z is less than or equal to 2. And the probability that z is less than or equal to 2 is 0.9772. And subtracting from 1 we get 0.0228. So the probability that their mean weight is less than 1.99 kilograms is 0.0228. Part 2. At the packing stage, these bags of flour are packed at random into consignments of size 100 bags. If 1,200 consignments are produced in a week, how many of these consignments would we expect to have a mean weight per bag of less than 1.99 kilograms? So expectation, we want to think multiply. There's an x in the word expect, which is a multiply symbol. The expected number of consignments with a mean weight per bag of less than 1.99 kilograms is going to be n multiplied by p. So n being our number of consignments and p being our probability that we got from part 1. Multiplying them, we get 27.36. Thus, we would expect 27 consignments to have a mean weight per bag of less than 1.99 kilograms. So even if this was 27.9, we would still round down because there's 27 full consignments that we would expect to have a mean weight of less than 1.99 kilograms.